So what we're going to look at is we're going to look at the sections from test 10, which are 19.2, 19.3, 20-1, 20-2, and 20-3. Now, just to quickly go over what each of these sections are and the formulas used before we begin. 19.2 was resistance, and the only formula we used in 19.2 was Ohm's law. If you need water at any point, okay? And nope. All right, 19.3 was the topic on power, and there were 3 formulas for power. Each of them are usable, or are not usable, are fair game, but you have to think about which of them you're going to use based on your parameters. These were the 3. Okay? P equals IV, where I is current, V is voltage. P equals I squared R, where I is current, R is resistance. Or P equals V squared over R, where V is voltage and R is resistance. Any of these still give you power. Okay? They all give you power, depending on what you're given in the scenario. We'll talk about that more. Now, in the next 3 sections, 20-1 through 20-3, it was all about schematics. Okay? 20-1 was just going over the symbols in schematics, which you use in 20-2 anyway. And then 20-3 talked about series and parallel circuits together, which built upon 20-2. So, lumping these together, these are just circuits. And there were a lot of formulas. I'm not going to sit here and list them all. Okay, they're all in your formula sheet. They're all in your notes. There was one other formula in 19.3 that I gave you guys. One other. Had to do with finding out how much it costs for energy. What do you got?
Equals energy times rate.
Good.
Which is actually P times T.
Very good. So this is in 19.3 still. And Eric is exactly right to say this next part, which she said is that this is also known as cost equals, now energy is defined as power times time. So you can write it this way as well. Okay? So replace energy with power times time, and that's what energy is, and the rate carries down. So if you're given a problem and you want to find the cost of a certain amount of energy, this is what you're going to use. But you have to remember about your units. Your rate is always going to be in dollars per kilowatt hour, which means that your power needs to be in kilowatts and your time needs to be in hours. So if you're given time in minutes, like 30 minutes, that's a half an hour. Okay? If you're given a time of 20 minutes, it's a third of an hour. You can convert by just dividing by 60. If you're given units of power in watts, you need to move the decimal spot 3 points to the left to make it into kilowatts. So remember your units, okay? And I was mentioning this a little while ago to somebody. If I were studying, one of the key things I always do when I was a student in physics was literally write out my formulas and write out what they mean, what each variable means, what each variable's units are, and then a little description of when I would use that formula. So for example, here, for V equals IR, if I were taking my own notes or studying, I would say, this is called Ohm's law. I would say that V is voltage measured in volts, I is current measured in amps, R is resistance measured in ohms. And I would say, this is used a lot when we're given 2 over the 3, or it's also used with our circuits. Remember, once we simplify the circuit to get one resistor, we can then use Ohm's law. So that's how I would describe that formula. And that's a way to study. It's a way to think about what's actually happening, because on the test, you need to know what to do with the formulas, not just what they are. Okay? So again, you're given these. I'm going to give you, I decided about 3 minutes ago, I'm going to give you this formula also. Cost equals energy times rate. Okay? But you're going to have to know that energy is power times time. Okay? So you're going to be given, I'll give you this right here and I'll highlight it, what I'm talking about. I'll give you this one. Cost equals energy times rate. But you have to know that it's power times time. Okay? You have to know that energy is power times time. And that comes from another formula, by the way. If you remember, think back, I'll write it in light green at the top here. The formula power equals work over time. But work is just energy. So you could write this instead as power equals energy over time. And then if you solve for energy, you would take the T and move it on up. And you get energy equals power times time, which is right here. And this is given on your test, actually. So if you want to use the one that's given here, this cost equals energy times rate, solve for energy up here, move the T up, you get power times time. That's where it comes into play over here. Evan.
Is watts a lowercase w?
It's a capital W. It is also capital for work, so be careful. Okay? Remember, watts are a unit. They will come after a number. Work is part of a formula. There's not going to be a number in there.
Wait, Mr. Howell, I don't understand what you were just saying about the move the E up and then,
Solve for E.
right?
What do you get?
Oh, so then it's just P times T?
Which is what you just said.
Oh, I didn't understand what, never mind.
Okay?
Okay, yeah.
P times T equals E.
Alright. I thought you were saying something about moving the T and moving the P and the T. I don't know.
Just the T. All right. With that said, examples of what we're going to have to cover on this test, okay? First, I'm going to start by going over the multiple choice and conceptual ideas, and then what we'll do is take a look at the type of math problems you'll see. All right? And you can already kind of predict the math problems. That's normal. So, first, you need to know what affects the resistance of a material. And there were 4 things: the length, the material itself, the temperature, and the cross-sectional area. There were 4 things. We made a table out of this.
All materials all materials have effect on
Length, material, what?
Yes. But again, we need to know the relationship as well. So for example, as length increases, resistance increases. Like you need to know those relationships, okay?
As the temperature goes up,
So does resistance. As cross-sectional area goes up, though, resistance goes down. And then for material, it's just if the material is different, it affects it. Like zinc versus copper. What's that? Yeah. Oh, everything I tell you is in your notes. There's never anything that's not in your notes. Everything.
It's the very first thing you had in 19.
Okay? In 19.2. Yep.
Well,
4 things that affect resistance.
you have an 18.
Next.
You had like 18.
If I gave you a circuit, you'd have to be able to describe what's happening in the circuit. For example, like a battery going into a light bulb. The charge leaves the we did this in the lab yesterday, remember. The charge leaves the positive terminal with a lot of potential energy. It hits the light bulb. That energy is then converted into light and heat. It leaves the light bulb with no energy. Goes back to the battery. The energy in the battery that's chemical is converted back into potential, and the charge continues the loop. Okay? That also affects, remember that graph that we kept looking at? Remember this graph? Okay, where we had A, B, C, D, and we had a little bit of a diagram next to it. Okay? I'd recommend looking at this. This was potential energy versus location. Okay?
Where is that graph? Is that in our book?
This is in, I think, 19.2 and 19.3 notes. Both, yeah. It's also in your text.
So we need to know like how the graph.
You should know what's happening here. So the potential energy, again, leaves the positive terminal. It hits the battery. All the potential energy is lost, not to the battery, it hits the light bulb. All the potential energy is lost in the light bulb to light and heat. It then leaves the light bulb in the wire. It hits the battery, and once it's in the battery, it converts back into potential energy. Okay?
So it goes from potential to chemical to potential.
It goes from potential to light/heat to chemical back to potential. Okay? Again, potential in the battery leaving, light and heat in the light bulb, chemical back in the battery converted into potential. Okay?
So potential is right when it's about to leave, right?
Yes, that's the high potential.
The T point.
So A is when it leaves the battery, B is when it hits the light bulb, C is when it leaves the light bulb, D is when it gets back to the battery, and then A is when it leaves the battery again. Okay, and we went over this in class, so take a look at that.
We did?
We did indeed. We talked about something called EMF. EMF, and Helen was nice enough to look it up for us. It was, remember, electromotive force, but don't remember that, please, because it's not a force. Okay, EMF is really the amount of energy that's being given off, or the amount of volts that the battery can provide. But we remember that the EMF is always less than the terminal voltage. So say the battery can provide 9 volts of energy, or of voltage. Okay? 9 volts. But the battery has some internal resistance. So we're really going to feel on the circuit maybe only 8.9 of those. Okay, so EMF has to do with the energy of the battery, but because the battery is made of metal, it has some internal resistance. So what you're actually going to get out of it is a little bit less than what you actually have.
Wait, so EMF is always less than the voltage?
Other way around.
Oh, voltage is always less than EMF?
Yes. The EMF is the amount that the battery wants to give you. The voltage is what it can actually get.
Got it.
Okay, Thomas?
Why don't they just change the name if it's out of force?
The same
Really good question. I don't know.
Power
Yeah.
companies to energy.
I could look it up, Thomas. I'm not sure though.
Good one.
Not sure.
Thank you. I thought you were laughing.
All right. Know your.
Quick thing on
Go ahead.
EMF, so like, is that gonna be in a conceptual or that's gonna be in a
It's not going to be part 3, so it's 1 over 2. Okay. Know your laws of series and parallel when it comes to your resistors. Okay, and your. So just remember, in series, just add them up. Okay? In parallel, you have to do 1 over and add up all their reciprocals
And then -1.
and then take the inverse of both sides. Very good. Okay? So you'll get a fraction or a decimal on the right and take the inverse or do 1 over.
So series is
Is this test more math?
no.
Please say no.
I'd say it's about the same as always. A third, third, third. It's pretty much identical. There's 32 points in multiple choice. There are 30 points. 32 points worth of multiple choice. 30 points worth of short answer. And then 38 points worth of math at the end. It's always around 30 each. Depends on the test. Yeah, it's always that way. Always third, third, third. All right, we talked about what happens if there's no load-bearing element in the circuit. Okay? Remember, a load-bearing element is something like a resistor or a light bulb. It can take on the voltage. If there is not one, so let's say we have a circuit like this. So there's a resistor in play. So the current's going to leave the positive terminal and flow in the clockwise direction. Now, let's say for some reason this resistor is removed. Okay, there's no resistor anymore. And now the wire continues. Well, now what's happening is that there's nothing to slow down the charge. So there's a lot of charge. There's a very high I value now, which will cause the wire to overheat, and you get what's called a short circuit. So this right here is a short circuit. That's what a short circuit is, because the last class was confused between an open, close, and short. Open and close are different. This is a short circuit when there's no load-bearing element. Okay, what does a load-bearing element do? It dissipates the voltage. It takes the voltage and converts it. If there is no load-bearing element, this wire is just going to start to heat up, and then it'll eventually melt the wire around it, and that's where fires can start. We talked about short circuits. Okay? It dissipates the voltage.
Thank you.
Now, the other difference, though, is if we imagine now you do have a resistor, so you're good. It's not a short circuit anymore. But now you've got a break in the circuit. Okay, there's a break in the circuit. Okay? What kind of a circuit do we call that? Open. Because there's a switch, and the switch is open. So can electrons flow now? No, because there's like a big bridge here. You can't jump it. You can't just jump over it. So this is an open circuit. Right now, the room is in open circuit state. The lights are not on. There's no flow of electrons. The minute I close this switch here, so I take this switch and I close it so it looks like that now. Now the circuit is closed, the lights go on. Okay? Keep them off? Yeah. So the light goes on now. Okay? Again, when you close the circuit, the light goes on. When you open the circuit, the light goes off. It's opposite of what you would naturally think there. Okay? Keep that in mind, please. You need to know what resistance is and how to define it really. Who can tell me what resistance really is? Not a formula, but what is resistance physically? Think about it. Nicole. Yeah, it's something that slows down the electrons or opposes the flow or opposes the current, right? It acts like friction. What about power? Anybody remember our definition of power? Yeah, it's the amount of energy dissipated over a time period. In this case, it's the potential energy of the charge carriers, right, over the time period. So remember that power, again, power normally is defined as work over time, but as Chaz said, we can replace work with energy. But in this chapter, we've been saying that power is really the change in potential energy over the time. Okay? So this is what power is, work over time, but work is energy. We are specifically talking about potential energy over here. Okay, potential energy. If I gave you, let's say, if I said to draw a circuit and gave you components, you have to be able to come up with a circuit or draw one. So for example, I'll tell you what to draw and see if you get the same thing I get. Draw a circuit in series with 3 resistors. Draw a circuit in series with 3 resistors, each with different resistances.
Wait, draw a circuit.
In series Sabila.
Come on, you're a little behind
I'm
there.
trying.
You need to start at the beginning and not sit there. Draw a circuit in series with 3 resistors, and the resistors have different resistances. Also include a battery and a switch. A battery and a switch.
Is the switch open or closed?
An open switch. Good question. An open switch.
Alright, I think that's right. Got it. Can I draw it?
Good.
Hey.
An open switch.
Is this it right here?
Good. And there are variations that are correct. So yours does not have to look like Erica's that she's drawing on the board now. It does not have to look like this. She's putting her 3 resistors on the top loop. You could put one on the left, one on the top, one on the right. That works as well.
You go ahead and draw spelling things afterwards.
What?
Draw
Good.
spelling things.
That's funny. Put the switch there. It doesn't matter. That's good. I like that. Different.
What should I
You
draw?
have the switch.
I want to draw something funny.
Where's the battery?
Show that it's like closing. That's why I said this one's terrible.
Draw, wait, Erica. Draw what I always want to draw. Come on.
What do you always draw?
Food! Draw food! Do it! Erica.
Battery, resistor, switch.
It's a little mariachi frog.
Okay, but that you understand that.
No. It's a little mariachi frog.
I am.
Resistor.
Yep, perfect. Okay, so we've got, let's take a look at Erica's drawing here. And yours can be different. Battery, resistor, switch that is open. And another drawing. I don't know. Oh, mariachi frog, sorry. I didn't hear what you said.
Oh, it's mariachi frog time. Oh my god. You have 5 minutes left.
No, we don't. Let's examine.
29. Oh my god. We have 5 minutes left.
Okay, next.
Guys.
Next. Know the difference between materials that are ohmic versus non-ohmic. Section 19.2. Ohmic versus non-ohmic.
That was 19.2.
Yep. Also, be able to understand and discuss what a pentiometer is. P-E-N-T-I-O-M-E-T-E-R.
Isn't that
You have to understand what it is, describe how it works, and maybe give an example.
your voice cracks?
Steph. Question.
I was going to answer.
Oh,
It's a knob.
guys, let's listen.
It's a dimmer, it's a knob, it helps conserve energy.
But what is it in physics terms, guys? What is it? What's a pentiometer?
It increases
Hands. Nicole.
It
Okay, you could say increase. How about just change? It can change the resistance of an element. It's a variable resistor. Okay? How does it work? How does it work? Emmett.
Well, it's kind of a volume switch.
Stop talking, people. Listen. Emmett.
Kind of like volume. In
Okay.
regards to how you can change it to whatever, I guess, resistance you want it to. So.
Yeah, but how does it work, though? You're right. You can change it, but how physically? What did I tell you guys?
Does that turn out the resistance?
Okay, good. It changes the amount of electrons. It changes the current, which can change the resistance, but it also changes the contact between the metal plates. Okay? So when you're changing a dimmer, there's more or less contact between the metal, which changes the flow of the circuit. Okay, so it's a variable resistor. A variable resistor.
Changing the flow of the electrons in the contact of metal plates.
Superconductors. What's a superconductor? Who remembers that?
I got it. They exhibit.
Guys, we can't hear her if we're all talking. We need to listen.
They exhibit a certain amount of resistance in critical temperatures.
What kind of amount of resistance? How much?
A lot.
Almost none.
Oh, almost zero.
Okay. Superconductor exhibits almost zero, which is pretty much negligible, resistance below its critical temperature, which enables us to do something called supercooling things, or superclocking, or overclocking. So, for example, on computers and stuff, they get them down really cold so that they run faster. The colder it goes, the faster it runs.
Is that why Mr. Richard's office
Yes.
is -2 degrees?
There it is. The server's in there. It's got to be cold, or else it will overheat. The resistance would become too high, it would slow down everything, and everything would back up. Steph.
I.e. aluminum at 1.6 Kelvin.
1.9. Close.
1.9 Kelvin.
That's right. That was one of your prom set
Zero
questions.
resistance. I just started my problems.
Now, you mean just finished, obviously, right? Just finished.
That's what.
Of course. You also should know. You should obviously. I told you that graph. You should know with the potential energy, but you should know. Remember, we talked about circuits being open or closed if an element is gone. So remember, we talked about like Christmas lights in series versus parallel. How if one goes out, they all go out, or they stay on. Know what happens there and why. Okay. Yeah, be able to give like an example of that and go through it and explain what's happening to the circuit. Okay? We went over that in class, so take a look at your notes if you're having trouble with that one. Let's get into the math parts. I'm going to tell you the type of problems we're going to have. I'm going to hope that you do your problem set because the problem set has all types of these problems in it. Okay, so for examples, the problem set is the best way to look at it. Now, one of your examples is going to be to simplify a complex circuit, like we did at the end of the lab yesterday. So, for example, this is not what you're going to get, but for example, something like this.
This is obviously
Yeah?
a parallel circuit.
It's both. It's complex, right? That's why it's complex. Let's take a look.
That's why I said complex.
So, whenever you see a branch,
It's series. A parallel.
yes. So, ready? Follow the flow. Here we go. Leaves the positive terminal. There's a branch. So these are in parallel. Now, no more branch, no more branch. So this is in series. This branches. This is in parallel. No more branch. This is in series. Now, once you come up with a value for these ones, so let's say, for example, that these two values are 5 and 2, and these are ohms, and this is 1 and 6, and this is 7 and 3, you can figure out the R value of these two together by using your parallel law, which says...
And then
Very good. So you add the half and the fifth, which gives you 0.7. You take the inverse of 0.7, that's 1.4 approximately. So RP would be 1.4. So what you do is this. You literally erase this part of the circuit in your mind. Erase the whole thing, which I can't do because for some reason it's not working. Let's make believe I could erase it. There we go. It's gone. Now, you overlay that part of a circuit with one resistor. in its place, one resistor here. And that resistor has a resistance of 1.4 now, which comes from here. And if you do the same thing here at the bottom, if you're able to get rid of these two and make it look like just one resistor and get the value, you have another resistor there. And then you would have how many resistors? 1, 2, 3, 4 resistors in what?
Series.
In series. What do you do in series? Just what? Just add them up. Okay? So once you get rid of your parallel, well, first of all, you always look for series, but there's nothing we can do with series at all, because these are separate. So once we resolve our parallels, then we have 4 of them all in series, all flowing as one. Add up those 4 numbers, and you get your REQ, your equivalent resistance. REQ, equivalent resistance. Okay? No, we got 10 minutes though. 2:29 today. It's examined.
Is that how you find the voltage as well? Did you find
Well, you'd either have to be given, guys, good question for the test. He said, is that how you would find the voltage? Either you'd be given the voltage in the beginning of the whole circuit, or you'd be given the current, one or the other. And you could find the other one as a result of that. Now, when we look at just parallel circuits, okay, or just series circuits, we can then find the voltage and current across each of those resistors, which is like the examples we did in class. If you look at your examples, I'll tell you right now, I'm giving you a big hint. Look at your examples that we did in section 20-2. We did one in parallel, we did one in series. All series and all parallel, not combined. There will definitely be one of those on the test. Okay? One in all series or one in all parallel. Well, you have to do a bunch of steps. For example, hypothetically, I'm not telling you what it is. Say you had a battery and it was connected with 3 resistors like that. Okay? You're told that this has a voltage of 10 volts, 2 ohms, 3 ohms, 5 ohms. You're going to be asked several things for this kind of a question. You're going to be asked, I might give you a word problem and say like there are 4 resistors in series with a battery, draw a schematic. So that might be part A right here. Just drawing it, which you've done already. Part B or part A, whatever after that, might say find the equivalent resistance. Okay? So this is easy, right? What's the answer for the REQ for this one? Right away. 10. Why? You just what? Yeah, they're all in series. So if you wanted to find an REQ and redraw this circuit like this, with just one resistor instead, it would just be 10. And the voltage happens to be 10. Coincidence. Okay? These are in series. Your law in series says that R equals R1 plus R2 plus R3 plus ... So I added these 3 together to come up with the equivalent circuit. Now, with the equivalent circuit, you have the voltage, you have the resistance. V equals IR tells us we can find the current also.
So then it'd be 1.
Yeah, it's just 1. Because it's going to be 10 here and 10 here. 10 over 10 gives you 1. So in this problem, the current would just be 1 amp. Now, the follow-up to that, which is what we did in class, was find the amount of voltage that drops across each resistor. Remember, this is 10 over here, right? So if this has a certain amount of voltage in this one and this one, they're going to add up to 10. Because in series, our voltage is equal to the sum of all the voltages. These are all those laws we had. So at this point in time, what you can do is remember that your current in series is consistent. So I is always going to be 1. So if you want to go ahead and find the voltage across the first one, you would use I1 times R1. If you want to find the voltage across the second one, we did this in class. I2, R2, V3, I3, R3. But the key is to remember that I is the same in all of these. So it's 0.5 times 2 for series. For parallel, remember they switched, I and the V. Then you have, 0.5 times 3, 0.5 times 5.
Wait, why is it 0.5?
Because why did I say 0.5? I don't know. Thank you, Emmett. I don't know what I was looking at. Where did 0.5 come from? Should just be what? 1, 1, 1. Yeah, sorry. The amps, or the current, which is right here, we solve for, is the current in the system. Since it's series, it's the same throughout all of them. And take a look. What's the voltage across each? Turns out to be 2, 3, and 5 volts. which add up to 10. Okay? That's an example in series. We did one in parallel as well in your class notes. Look at both. Okay? You'll get one or the other, or you might get both, or maybe you'll get a choice. Okay? So think about that. But look at both. I would recommend looking at both. Helen.
Isn't it also proportional? Like, if it was.
It happens to be right now.
No,
So
even if it wasn't like, it was 20, the voltage was 20, but the other is the same.
yes, it is. It definitely is. But in parallel, you're going to see the reverse of that. So don't always use that law. But you're right. You're seeing that correlation.
In series it is. Oh,
Yeah, in series you're going to see the fact that it is proportional for sure. The other one is proportional of the reciprocals, so don't. So it's a lot more different. It's different. Okay, but yes, good note. All right, what else? Well, you have equivalent resistance. You're going to have a parallel or series circuit, and the last example you're going to have is going to be with power. Okay, so say for example, you have. Let's say we've got. The power that a light bulb uses is 1 kilowatt. And the resistance of the light bulb is 3 ohms. Determine the voltage. And I'm putting it in order, so do it in the order I put it in. The current. And the cost to operate for 15 minutes when the rate is, let's say 30 cents an hour. Or kilowatt hour, sorry. Okay? So this is what you're given. You're given the power and the resistance of a light bulb. And you need to find the following things. So, for power, you have how many formulas you can choose? 3. You have R, you have P. You're looking for V. P, V, and R. Which formula, Tristan, for P, V, and R? There you go. That's the one you're going to use. Because, remember, you can use any of them. But you have P, you have that. But what does P need to be in? What units? Watts. No, for cost, it's kilowatts, Erica. For regular stuff, though, that we're doing here, these calculations need to be in watts. So a kilowatt is...
No, don't you move it over to the right?
There it is, 1,000 watts. Kilo means 1,000. If you're going from kilo to regular, you have to put 1,000 in front of it. So that would be 1,000 watts for the power. The resistance would be 3. So you'd move the R up. Okay, so we'd have 1,000 equals V squared over 3. Move the 3 up to make that 3,000. And then take the square root of that answer to get the voltage. Okay?
And then current.
Okay, then to get the current, you now know the voltage. So somebody tell me square root of 3,000 real quick? Square root of 3,000?
You can't do it in your head?
I can get an estimate, but it doesn't always, I want an exact value.
I'm going to see 4.7.
Okay. So that means that the voltage would be 54.7 volts. Okay, that's part A's answer. Now, take a look at part B. Part B wants the current. Well, the current is the I value, right? Just use V equals IR. Use V equals IR. You know the voltage is 54.7. You know the resistance is 3 ohms. So 54.7 equals I times 3 ohms. Solve for I. So you do them in the order I'm giving you. Now, one thing I told the other class. If you can't get part A for some crazy reason, you need it for part B, don't you?
Yeah.
So what do?
Make it up.
Yes, make up a number for part A. So what? You get part A wrong, but you could at least get part B right based on your wrong answer. You don't ever get double jeopardized. So if say you came up with your answer for part A and you got 20 volts and not 54.7, you got 20, okay? And then you did the right work in part B, I would still give you credit, obviously, okay? Part C, make sure you look at your notes. We did an example, okay, for part C. Power times time times rate. It's watts, not work.